Okay, today we cover section 8.2 in the textbook, and we look at relationships between Kw, Ka, and Kb, as well as formulas for pH and pOH. So, you'll recall from the previous lesson that the general formula for acid ionization, I believe in the earlier one I wrote HX, so here I've chosen HA. For Arrhenius theory, I'm showing the dissociation into, or the ionization into H positive and A negative, the anion. And for the Bronsted-Lowry theory, I'm showing the proton donor HA, donating a proton to H2O, forming the hydronium ion and the conjugate base of HA, which is A negative. So both of these are equations to describe the behavior of acids. When you write the Ka for the Arrhenius equation, you'll see we have the hydrogen ion in the numerator. And when we write the Ka for the Bronsted-Lowry equation, you'll notice that we have the hydronium ion. So whether you choose to write the Arrhenius or Bronsted-Lowry equation, I'll leave up to you. However, you are responsible for both. And you'll find that all the formulas that I carry through in the lesson follow the Bronsted-Lowry theory, and that's because we believe the hydronium ion to be a truer representation of the particles in solution. So remember, the magnitude of K indicates the extent of the reaction, right? The concentration of products compared to reactants. So if you have a Ka value that's very, very, very large, then the reaction is essentially complete, and that's the behavior of strong acids. They'll essentially have all ions in solution. If you have 100 molecules of HA, then you'll have 100 hydrogen ions and 100 anions. Bases, even though I haven't rewritten the general formula for the base dissociation, when Kb is very, very large, again, 100% dissociation or ionization for the strong base. Now, weak acids, what happens when Ka is less than 1 or not very, very large? And the idea here is that that's where equilibrium is established. So when you're looking at a solution of hydrochloric acid compared to a solution of acetic acid, they both look like water. The equilibrium system is happening in the solution of acetic acid. The acetic acid molecule is largely present and interacting with water through proton transfer to form the hydronium and the acetate ion. But really, that ionization is about 1.3%. And so we have mostly HA molecules and very few ions at equilibrium. And so that's why I've written all entities are present, but there are very few ions because there's very low ionization. And the same happens for the weak bases. Okay, so let's explore then the self or autoionization of water. So you may recall this from a Bronsted-Lowry example. You earlier predicted the products when water behaves as both a Bronsted-Lowry and acid and base. And now I'm showing you here the expression for K here, which you also wrote in that earlier lesson, but we're calling it Kw. So that's the ion product constant for water. And you'll notice that we omit the reactants that are both liquids, and therefore it's just a product. No, there's no quotient. So for solutions at 25 degrees Celsius, for water at 25 degrees Celsius, we've been able to measure the hydronium and hydroxide ion concentrations, and it turns out they're equal, 1.0 times 10 to the negative 7 moles per liter. And so if we follow this formula, determine Kw by multiplying the hydronium and hydroxide ion concentrations, we'll see that we get 1.0 times 10 to the negative 14. As usual, Kw does not have any units, no value of K we assign units, because it is the magnitude that is important. And so we see the product of those ions to be 1.0 times 10 to the negative 14. Ultimately, in any solution, if the hydronium ion concentration is greater than the hydroxide, then that solution will be acidic. You can see here that the hydronium and hydroxide are equal, and in that case, the solution will be neutral. So distilled water would have a neutral pH. pH of 7. In the case where the hydroxide ion concentration is greater than the hydronium, the solution will be basic. And just keep in mind here that you can manipulate this equation here to solve for example, the hydronium ion, if you know Kw and the hydroxide ion concentration. Right? Keeping in mind that Kw here is always 1.0 times 10 to the negative 14 at 25 degrees Celsius. And similarly, if you needed to find the hydroxide ion concentration and you knew the hydronium, then you would be able to isolate and solve for the hydroxide ion. Okay, so let's look at the relationship then between Ka and Kb for a conjugate acid-base pair and Kw. So pause the video and take a moment here to predict the right side of both equations. HA is going to behave as a Bronsted-Lowry acid, and A negative, right here, is going to behave as a Bronsted-Lowry base. Okay, so following the proton transfer, the first reaction produces hydronium and A negative, and the second produces hydroxide and HA. All right, write expressions for Ka and Kb of both reactions here. Okay, you'll notice I omitted water in both cases. Now algebraically add the two equations below and write your target equation here. So don't manipulate these, just literally add them as is, okay, and write the sum here. Okay, so you'll notice that the HA and A negatives cancel and we come up with the autoionization of water. So if you'll recall, Kw comes from that equation and we're able to write the hydronium times the hydroxide ion concentration. So what's the relationship between Ka, Kb, and Kw for a conjugate acid-base pair? Well, look at this quotient and look at this one and see if you can come up with a mathematical operation that will produce this answer. Okay, so you'll see here that when I multiply Ka and Kb, the A negatives cancel, the HA cancel, and I finish with the hydronium ion times the hydroxide ion. And isn't that the expression for Kw? It certainly is. And so for a conjugate acid-base pair, Kw equals Ka times Kb. Remember Kw, right, is always 1.0 times 10 to the negative 14. So you can isolate Ka or Kb if you know the other one in order to find Kw. So why don't you take a moment and look up in your textbook the Ka of hydrofluoric acid. Okay, and after that, once you've looked that up, you will not find the Kb value for the conjugate base of HF. You will not find the Kb of the fluoride ion in the Kb table. But given that Ka value and knowing Kw, you can solve for Kb by isolating Kb from this formula, and then plug in Kw and Ka for hydrofluoric acid and determine Kb of the fluoride ion. So look up the Ka value for HF and find the Kb value for the fluoride ion. Okay, so you'll see that Ka was 6.6 times 10 to the negative 4, and to solve for Kb, I isolated Kb from this equation, Kw divided by Ka, plugged in the values, and we end up with 1.5 times 10 to the negative 11. So when you saw a Ka value of negative 4, did you think, times 10 to the negative 4, did you think that HF was a strong acid or a weak acid? Hopefully you're thinking a weak acid. The Kas for strong acids will just say very, very, very large. They're not even quantified. When you see the Kb value of 1.5 times 10 to the negative 11, does that also seem weak? Weaker, in fact, so it's a weaker, the conjugate base is weaker than the weak acid. but they are both considered weak. Okay, so here's a schematic that is challenging to understand. The key is to read it first vertically and then horizontally. So let's have a look at the red and recognize the relationship here amongst the acids. So HCl is listed at the top as a very SA, strong acid, and you can see the arrows indicating strength of acid up here. HF comes down, so maybe I better label this here. So this is a strong acid, right? Whereas HF is a weak acid. Now NH3, way down at the bottom, is a very weak acid, to the point where it does not donate a proton. Okay, now let's read the blue side, right? And we have NH3 at the bottom. Well, actually, it should be near the bottom because this is still considered a weak base. And the acetate ion is also a weak base. Now, I didn't list the very weak base, but let's now read this across. So what do I mean by reading it across? Well, when you look at this HCl, read across, what is the conjugate base of HCl? So HCl is the acid, donate a proton, lose the H, and lose a charge, and what particle do you form? So what is the conjugate base of HCl? Hopefully you're thinking Cl negative. Try it again with HF. What's the conjugate base of HF? Hopefully you're thinking F negative. Let's go the other way. So looking at this base, what is the conjugate acid of the acetate ion? And hopefully you're thinking of acetic acid. Okay, NH3 is a weak base. What is the conjugate acid of NH3? Have it accept a proton, and we form the ammonium particle. Okay, last one. Here's the acid, although it's so weak we don't even, it doesn't even react, but here's a very weak acid. What is the conjugate base of NH3? So hopefully you're coming up with, NH2 positive. So that's what's left over after NH3 donates a proton. So does NH3 donate a proton in solution? No, it doesn't. It's such a weak acid that it does not, this essentially does not react. And as you read across, you'll notice here that the conjugate base of a very weak acid is actually a very strong base. So for the very strong base, we think complete reaction here. Okay, so that's a certain point in our table here. I'm just going to draw a line here and I'll draw a line here because this section in the middle, these are where the acids and bases are weak. So you'll notice at the top above the black line that HCl is a very strong acid. The conjugate base of a very strong acid is so weak, a very weak base, that just like the very weak acid does not react, this very weak base does not react. And the calculations that you do with this formula here actually support that. So the product of Ka and Kb has to be 1.0 times 10 to the negative 14. Well, if you're going to solve for Kb of the chloride ion, you'll need to take Kw and divide by Ka. Well, Kw is 1.0 times 10 to the negative 14. The Ka of HCl is very, 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 very large. They don't even quantify it for you in the table. So if you're going to take this small number and divide by an incredibly large number, are you not essentially going to approach zero? And that's the idea here, that the Kb value would essentially be zero, and therefore that reaction does not occur. And so we learn here that the conjugate bases of strong acids are so weak that they do not react. We learned that weak acids have weak conjugate bases, and so both of these will establish equilibrium. And we learned that strong bases have very weak conjugate acids, essentially to the point where they do not react. Okay, last comment or section here now is about pH and pOH. So they both stand for power of. So we're talking about the power of hydrogen or the power of hydroxide. We've seen earlier at 25 degrees Celsius that the concentration of hydronium and hydroxide are 1.0 times 10 to the negative 7. Well, there's nothing very convenient about that scientific notation number. And so the point of pH and pOH is to have a more convenient way using just positive integers to communicate those concentrations. So we can state the concentration of hydronium, or we could just state the pH, or the pOH for that matter. So first formula then, we look at the pH formula. And you'll see here that pH is equal to the negative log of the hydronium ion concentration. So we will need to be using that in our with our calculator, and you'll see you have a log function on your calculator. Now I can see here that I have messed up the numbers a little bit, so just a moment. Okay, sorry about that. Now these are listed properly. So equation number 1, you'll see, is our familiar one of hydronium and hydroxide, the product being equal to Kw, which we know to be 1.0 times 10 to the negative 14. Now, to calculate pH, you're going to use the log button on your calculator. It'll be the negative log of the hydronium ion concentration. So the idea is that a log is an exponent. So if a log is an exponent, we're basically saying that the pH value is the negative of the exponent on a base of 10 that equals the hydronium ion concentration. So in other words, the base is 10 and the exponent is the negative pH. And so we can rewrite equation 2a as equation 2b, where the hydronium ion equals 10 to the negative pH. And so if you know the pH and you need the hydronium ion concentration, then you'll use this formula. If you know the hydronium ion concentration and you need the pH, you'll use 2a. Same thing happens for pOH. We can calculate pOH by the negative log of the hydroxide ion concentration, or given the hydroxide ion concentration, we can calculate given the pOH, we can calculate the hydroxide ion concentration. Now, to get equation number 4, we'll look at a quick derivation over here on the right. So if we were to take the log of both sides here, we'd be looking at the log of a product here equals the log of 1.0 times 10 to the negative 14. Remember, logs are exponents. And so if we're looking at, think of your rules of exponents or laws of exponents. When we're multiplying powers with the same base, we add exponents. And therefore, we would add the concentration, the log of the concentration of hydronium plus the log of the concentration of hydroxide. Remember, a log is just an exponent, so we're adding exponents on the same base, right? Because we're multiplying the powers here. And so that'll equal the log of 1.0 times 10 to the negative 14. Now, let's multiply by negative 1 on both sides. And so we're going to essentially distribute a negative 1. So we'll have the negative log of the hydronium ion plus the negative log of that hydroxide ion, and that will equal the negative log of 1.0 times 10 to the negative 14. Now pull out your calculator and actually do that. Negative log of 1.0 times 10 to the negative 14. You'll find that that equals 14. Now, what could we replace the negative log of hydronium with? Well, that's pH. Remember equation 2a here. And if you look at equation 3a, the pOH is the negative log of the hydroxide ion concentration. And so there's our fourth equation, that the sum of the pH and pOH must equal 14. Okay, just a comment about sig digs. The concentration itself has a certain number of sig digs. When you do the significant digits for pH, focus in on the digits after the decimal, because the digit in front of the decimal is really just place holding the power of 10. Now, just to give you a picture here of the pH and pOH, where that sum is 14, if you have that horizontal line where we normally label pH and pOH, if we do the pH here, you're typically thinking of it running from 1 to 14, with 7 as being neutral. So what happens with the pOH values? Well, if pH is 1, then 1 plus 13 will equal 14. If the pH is 7, then 7 plus 7 will equal 14. If the pH is 3, then 3 plus 11 will equal 14. And so you can see that the pOH, when the pH is 14, the pOH is 0. And so, just like before, when a solution had a pH greater than 7, the solution was acidic. And so when the pOH is greater than 7, the solution is acidic. And same thing here, we're used to a pH in this range being basic, right? Now you're learning that a low pOH means a basic solution. Okay, so that's really it. We just keep those equations 1 to 4 in our toolbox and our mental toolbox, and we can go ahead and do calculations. So I've done a couple of examples here. You'll find the textbook breaks up these questions. I'm trying to combine a few to shorten the video. So you're being asked to calculate pH and pOH of a solution with the hydronium ion concentration of 2.2 times 10 to the negative 5. So hopefully that's drawing to mind the equation where if you know the hydronium ion concentration, you can calculate the pH. And so we're looking for the negative log of 2.2 times 10 to the negative 5. So we find that the pH here equals 4.66. Notice in terms of sig figs that I had 2 sig figs in the concentration, and so I have 2 digits after the decimal. There's the 2 sig figs in the pH. Now we need to calculate pOH. Well, pH plus pOH equals 14. So and I'm going to keep 2 digits after the decimal there for sig figs. So if I'm going to solve for pOH, I can just take the 14 and subtract the 4.66. and come up with 9.34. So again, 2 digits after the decimal for the subtraction, so I maintain the 2 digits. Now, was there another way to do that? Well, knowing the hydronium ion concentration and using Kw, we could have solved for the hydroxide ion concentration by Kw over the hydronium ion. Knowing hydroxide, we could have then calculated the pOH from the negative log of the hydroxide ion concentration, and then found our pOH by 14 minus the pOH. So that's a 3-step solution. Of course, we choose the 2-step, and I think that's probably the one that's more likely to come to your mind. But just be aware, I find people often forget about this equation here, right? Or some form of this equation. So don't forget about equation number 1 in your toolbox. Okay, last question here. Calculate the hydronium ion concentration and the pH for a solution with a pOH of 2.47. So give that a try using any formula from the toolbox there from 1 to 4 and see what you get. Okay, so you'll see here that I've solved it 2 different ways. Given the pOH, I was able to first find the pH, note the 2 digits after the decimal, and then the hydronium ion concentration by equation 2a, 10 to the negative pH. Alternatively, I could have found the hydroxide ion concentration by 10 to the negative pOH. Notice I didn't round here because I am looking to determine the hydronium and the pH, hydronium ion concentration and the pH, and I've done so and rounded for each of those. And so applying Kw over hydroxide and then the negative log of the hydronium ion concentration, you'll see we're coming up with the same pH and the same hydronium ion concentration as the first solution.